He came up to me one day and he's like, everyone has a butt and everyone has a big one. I'm like, what do you mean by this?
What does this mean?
I was like, Jackson, what are you trying to say? That's too funny. Oh my gosh. Hi, Lauren.
Okay, cut 7 off your list of problems. That was a mistake on my part. If you have a question on 7, yeah, just cut that one from the list. Anybody have a question on something other than 7? Yes.
20.
20.
Yeah.
So let f of x equal cosine x, and let g of x equal sine x. So we're supposed to do f plus g of 180 degrees. Then we're going to do f minus g of 180 degrees. And then we're going to do f times g of 180 degrees. So in every case, we're going to have to find f of 180 and g of 180. So we have cosine and sine. 180 degrees is a point on the circle to where you can't possibly make a triangle. So your only way to go about this is to, well, I guess go over to 180 and interpret every point on the unit circle as some cosine, comma sine. So this guy here, left one up 0, this is at 180 degrees. And he is cosine of -1 and a sine of 0. So f of 180, which is cosine of 180, that's going to be -1. And g of 180, which is basically sine of 180, what it is sine of 180, that's going to be 0, because every point on the unit circle is cosine, comma, sine. So at this point, we just have to plug in. So the first one is the sum of those two, that's -1 plus 0. The second one is the subtraction of those two, that's -1 minus 0. The third is the multiplication of those two, and since the 1 is 0, when you multiply, you get 0. Those are the three. If ever you have an angle that's a multiple of 90, like 90, 180, 27, this is how we go about it. Other questions? That's it? Great. Thank you. So, let me remind us of what we did yesterday. When we discussed symmetry, we said, should I have something that is symmetric about an axis? Like in this case, this guy's symmetric about the y-axis. The uniqueness of him is that while there may be a point over here at A comma B, when I flip him, he's going to be exactly the same. When I flip him about the y-axis, he's going to look exactly the same. So this guy over here has got to be -A comma B. In other words, if you sub in -x for x, and the function is the same, then that means you have y-axis symmetry. If the function isn't the same, well then what you did is reflected that function about the y-axis. And you could take any function, like y equals 2x plus 1, And if you replace negative x for x, in this case you'll get y equals negative 2x plus 1. Notice they're different, not symmetric. But this is basically the result when you reflect about the y-axis. Plug in negative x for x, that reflects you around the y-axis. What does this graph look like? Same y-intercept, but a negative slope. And if you reflected this guy about the y-axis, that's what you get. What's up and to the right will be over here to the left, and what's down and to the left is going to be over there to the right. Make sense? Okay, now let's talk about translations. Translations are going to be moving functions all around, moving them around. And let's go to a familiar equation. Like y equals x squared. When we talk about translations, that's a fancy word for shifting up, down, left, and right. Just take a picture, move it up, down, left, right, some amount. You're not going to be changing the picture in any way in terms of its shape, you're just going to be picking it up and moving it from one place to another. And like I said, let's think of a simple function like y equals x squared. Now, you guys may remember what this looks like. It's a parabola, but at the very least, when x is 0, y is 0. Look at the equation there, when x is 0, y is 0. When x is 1, y is 1. When x is negative 1, y is also 1. When x is 2, y is... x is 2, y is 4. Negative 2 would also be at 4, because what, negative 2 times itself is 4. And then over 3, up 9. You got this guy that you know pretty well. Right? He looks like that. That's y equals x squared. It's a parabola. What if I wanted to shift this guy? What if I wanted to shift him to the right? What if I wanted this 0 point to move from here to there? Here's what I want. And I'm going to have to figure out how I pull this off. I want the 0 point to be moved over to 2. In other words, I want to shift this guy right 2 units. Let me write the equation for this, and I'm going to ask you to think about it, and then you should agree with me that the equation will make this parabola, because here, the 0 point, instead of being at 0, is now at 2. What if I had this function? Take a look at that for a second. Do you agree that the 0 point is now moved to 2? Look at that equation. Plug in 2 for x, what do you get? 0 squared. Plug in 3 for x, what will you get? 1 squared. Plug in 1 for x, what will you get? 1, negative 1 squared. Notice how you'll end up with the exact same points. You'll just move the whole thing to the right too. How did we move it to the right too? Instead of seeing x squared, we saw x minus 2 squared. Plug in 2, you'll get the 0 point. Plug in 3, you'll get the point that used to be at 1. Plug in 1, you'll get the point that used to be at negative 1. And if the point at 1 is the point that used to be at negative 1, everything's been basically shifted 2 to the right. How did we do this? We substituted x minus 2 for x. That's what we did, right? We put where we saw x, we now see x minus 2. And that's going to say, well, every value that I put into x is now going to read as x minus 2. So what was at 0 would now be over at 2. What if I wanted to go left 2? Well, better yet, what if I wanted to go up 2? What if I wanted to go up 2? I want to take this parabola and shift him up 2 units. Let me first, I'm going to write this down in one way that's going to look strange. I'm going to start by writing it like that, y minus 2 equals x squared. And then I'm going to solve for y. Think about what's going to happen here. Every value that I would get out of here is now going to be the same value plus 2. So when I put in 0, what am I going to get out? Put in 0, get out 2. So I'm going to be up here at 2. Put in 1, what are you going to get out? 3. Put in negative 1, what are you going to get out? Negative 1 times itself? 1. Plus 2? 3. You get the same parabola. But he shifted up 2 units. All I did was take every value I get out of here and just add 2 to it. So all the values are just going to move up 2 units. Instead of getting out 0, I'll get out 2. Well, the output is my y. That means my y's have just all been increased by 2. How did I pull that one off? I did it subtly here. What I did was I substituted y minus 2 for y. And that will move me up 2 units. Because instead of y equals x squared, I did y minus 2 equals x squared. I solved it out to make it look pretty. But really what I did to pull that off was I substituted it. And when I sub in the y minus 2, I then add 2 to both sides. And what I end up getting is the same function with 2 added to each value. So everything that comes out is always 2 more. And that just moves the whole parabola up. But you can actually, there's kind of a pattern here. Because you might wonder, if subbing x minus 2 for x moves me right 2, would subbing in x plus 2 move me left 2? I mean, think about this for a second. We don't even need to make a graph of that. Where's the 0 point going to be? X equals, what is going to give me that 0? X equals negative 2. Yeah. So x equals negative 2 will give me y equals 0. Well, that's going to move my guy over to there. So it appears that when I sub x plus 2 for x, that's going to move me left 2. Really, if I subbed x plus anything, that's going to move me left that number of anythings. And if I subbed an x minus anything, that's going to put my 0 point over to the right. Same thing with the up. Because think about it. What if I wanted to go down 2? What if I wanted to go down 2? Rather than plugging in y minus 2, I'm going to plug in y plus 2. Let's see what happens. Solve for y. What's this equation? It's a parabola with every output with 2 taken away. So what came out before as 0 is going to come out now as negative 2. What came out before as 1 is going to come out now as negative 1. Everything's going to be, take the original function values, the original outputs, the original y's, and just take 2 away from them. That's going to pull down the function. And to pull down the function, we sub y plus 2 for y. So interesting. To go right, we subbed. To go right 2, we subbed x minus 2 for x. To go left 2, we subbed x plus 2 for x. Notice, to go right or left, we substituted in a different x. Does that make sense? Right? To go right or left, we subbed in a different x. And to go up or down, we subbed in a different y. That makes sense too. Let me put this all in one box. So if we sub x minus h for x, that's the one that pushes us to the right. h units. That moved us to the right h units. What if we sub x plus h for x? When we subbed in x plus h, now our 0 is going to be at negative h. Our 0 is going to be off to the left. That's going to move us left h units. When we sub y minus k for y, well, when we subbed in y minus 2, that moved us up 2, because we ended up adding 2 to both sides, and we got the same function values plus 2. Well, subbing in y minus k ended up moving us up k units. And subbing in y plus k for y moved us down k units. But with this box of tricks here, I should be able to take any function and move it any amount. I can move it up, down, left, right, side, whatever. I mean, I can move it all over the place by just making simple substitutions. Is that a stomach? Was it? It's almost lunchtime. Your body actually gets into a rhythm of eating at a certain time of day. So it'll start producing digestive enzymes in anticipation of the food entering. Because if the digestive enzymes weren't produced until the food actually hit the stomach, the food that would hit the stomach first would be digested poorly compared to the food that would come in the stomach last. When you smell food and you get hungry, it's the same reason. Because the smell of food makes your brain anticipate eating food, and in anticipation of eating food, your stomach will start producing digestive enzymes. Just an idea of why and if you do it at a certain time every day, you'll get hungry at that time, should you not eat. So just that gives you an idea. Maybe you do that with like a pet at home where you always feed them at the same time of day. Your brain is in some ways not much more complicated than the pet's when it comes to the hunger mechanism. If it's every time of day and you're doing it regularly, your body will adapt. Just like the cat or the dog's body will adapt. So, here we go. So we have this function. By the way, anytime a function is written in this f of x notation, you could always just take it back to the y notation if you wanted to. Like, if you wanted to. It really, like, you put in x, you get out that, okay, well then, that's what you get out, that's the same as the y. Any function, I can write the equation of a line like this. I could write the equation of a line like that. They're really it's the same thing, because, I mean, think about this function. Put in 0, get out 1. Put in 1, get out 3. Put in 2, get out 5. Feel familiar? That was pre-algebra, right? Well, at least algebra 1, where you did that. So it's really the same thing. Now, what if I want to shift this by translating it? What if I want to translate it up 2 units and left 3 units? What am I going to have to do to make it go up 2 units? I'm going to have to sub in y minus 2 for y. That's what I'm going to have to do to make it go up 2 units. Personally, my personal opinion, I wish it was y plus 2 for up 2. Because plus 2 seems more like up than minus 2. But I always remember, when it comes to symmetry, reflections, and translations, it's always the opposite of what I wished it would be. I wish you'd plug in negative x for x to do symmetry around the x-axis. Doesn't work that way. You plug in negative x for x to check symmetry on the y. Same thing here. When you do y minus 2, that's going to move you up 2. How do you go left 2? You're going to plug in x plus 3 or minus 3? X plus 3 for x. So take the original function, like this, plug in y minus 2 for y, plug in x plus 3 for x. Where you see x, take out the x, put in an x plus 3. Where you see y, take out the y, put in a y minus 2. Then resolve it out. Add 2 to both sides. There it is. If you started looking at this function, by the way, this is a good function to have a picture of in your head. It's the easiest example of a particular type of function you'll see in calculus. Put in 0, you'll get out absolute value of 0. 0. Put in 1, you'll get out. Put in 2, you'll get out. Put in 3, you'll get out. Okay, what about if you put in negative 1? 1. Put in negative 2. Put in negative 3. It's like a V. That's a good one to have in your head. Just, you know what a parabola looks like, y equals x squared. You should know what y equals absolute value of x looks like in your head. And I say that because this is an example that comes up a lot in calculus because it's the simplest, it's the most well-known example of a particular type of function. Yep.
Like how we used to do like over 2 up, or over 3 up 2,
Mm-hmm.
and then we did like, you could just rotate a certain and walk. Can we do that with these two, or no?
You could, I mean, you could assign every point on that rather than as any point on the xy plane could also be written like that, any point. So yeah, you could look at every one of those points rather than 1, 1. You could look at it as square root 2 at a 45-degree angle. Right, because if you think about this for a second, that would be true. Because over 1, up 1, it is the 45, 45, 90 triangle. And it's hypotenuse the square root 2. If you can see that in your head, or at least imagine that, you have done a really good job of understanding what's going on. And yes, you could take every point and put it in that form if you wanted. You will find that this form is not always useful, but when it is useful, it's normally very useful. So, I know that makes sense. And when this is useful, it's normally very useful. The nice thing is you could do either. The nice thing about this one is 1, 1 is only able to be described as 1, 1. The less nice thing about this one is I can describe any point infinitely number of ways. Or maybe you say that's the nice thing about it. Because in certain cases it might be nice if you could pick what your angle is. When you start dealing with complex numbers, which we haven't done much of on the plane, but we will get to that point, where, because you like, when you have something like this, right? We'll start doing this eventually, where to make a picture of this number, since that number does not exist on the number line, the one thing we start to do is put the real number portion here and the